Right. Before anything, I would like to thank the Institute for the invitation and also the audience for coming. So as Gerald said, I will be talking about polynomial ergodic theorems for strongly mixing commuting transformations. But before talking about the polynomial ergodic theorems, I will talk a little about weakly mixing polynomial ergodic theorems. So the first thing is to talk about the mode of convergence. So the mode of convergence which I'm interested in is called convergence in uniform density. And what it is that if we're given a sequence xn with index on z, which comes in a metric space, in a compact metric space, then we write usually lim of xn is equal to x. If for every epsilon larger than 0, the limit here goes to 0. So what this limit is counting is how much of the time dxnx is larger than epsilon, and we want that to be 0. So a way of thinking of this is that 0% of the time dxnx is far away from x. Sorry, xn is far away from x. Okay, so another way, an equivalent way of defining this is by using a strong Cesaro average, like the one here. The only thing that one has to be careful with is that here I have compactness. Without compactness, that is not true. Okay, so that's a mode of convergence. So of course, the usual limits are stronger than limits in uniform density. An example of why this is the case will be a small that limits allow us to have a set of exceptions. For example, the set 2 to a k in n, which is very sparse. And we can define a sequence xn to be 1 when n is in the set 2k in n, and xn to be 0 otherwise. And then when we take the UD limit of xn, what happens is that because this sequence is so sparse, essentially 100% of the time xn is going to be 0. A more interesting set of exceptions for a UD limit is a set of finite sums, 10 to the k in n. So this set can be thought of as the set of whole numbers made up of ones and zeros in base 10. So it's also very sparse, and we can define the sequence, where is the sequence? Xn to be 1 if n is in the set of finite sums and 0 otherwise. And then when we see how much percentage of time xn is close to 0, it turns out to be 100% of the time. Now, what is very interesting about these sets of semi-sums, finite sums, is that the first set was infinite, but it has no algebraic structure at all. The second set has as much algebraic structure as one might expect in Z, because if we had more, we would have a group, right? Or a subgroup of Z. So that's as good as it can be. Now, the first weakly mixing polynomial ergodic theorem is due to Bergelson, and this comes from 1987. And what it says is that if we have L polynomials V1 through VL in Cx, and all of them are non-constant polynomials such that for I different from j, bj minus bi is non-constant, and also the polynomials were non-constant to begin with, then if this happens, we have that any weakly mixing variable probability preserving system xnut will have this limiting formula for any sets A0 to AL. So what the limiting formula is saying is that essentially 100% of the time, the multi-correlation expression here is close to being independent. Now, 100% of the time means that there are exceptions, right? And potentially, because this is just a limit in uniform density, we could have some sequence of times that take this multi-correlation expression away from independence. And how intense or how extreme is this phenomenon? Actually, it is very common. So the generic weakly mixing T from 0,1 to 0,1 has the property that for any epsilon larger than 0, one can find increasing sequence in k in n, such that for any t in n and any k1 through kt, we have that this multi-correlation expression here will be close to being close to this expression here, and that is for any sums of this form. So first things first. So the numerical structure that we have here is a set of finite sums, right? So it is the set of finite sums of nks. Second, what is this thing close to? It is close to total dependence, right? So here we have independence. Here we have what will be considered total dependence. And as it says here, this is what happens generically. So when one takes Euler limits of weakly mixing transformations, one should expect to see many non-independent times.
Just let me remark that the easiest way to feel what you said is if you i's have 0 at 0, then the right-hand side is just mu away instead of mu to the power L plus 1. That's extreme form of dependence, as you said.
Right, right. And then there's also another way of dependence, which is bad, which is they could be disjoint, right? So if you take a Roglin tower, you could translate this by 1, this by 3, and then you will have intersection being empty. So it can be bad, right? It doesn't have to be independent. It can be even 0 or be mu of A. So, all right. So now that's not the only weakly mixing pet that we have. We have many more weakly mixing pets. So I will be stating special cases of several results. The first of these special cases follows from a result of Bergelson and Leibman from 1996. And what it says is that if we have L polynomials in ZX, which are non-constant, and we take L commuting transformations with the property that for any A1 through AL in ZL without 0, the product in here is weakly mixing. So if that happens, then we have that the U limit of this expression goes to independence. So the assumption here is very easy because we are assuming that our transformations have as much mixing as one can expect, at least at linear level, right? So the whole group generated by T1 through TL has the property that if the element is not 0 or the identity, then it is weakly mixing. So that's why we don't need assumptions. But if we want, for some reason, we want to reduce the amount of weakly mixing assumptions on T1 through TL, we will need to know more about V1 through VL. And what I will do now is I will state two extreme cases of this type of assumptions. So the first case is another weakly mixing theorem, which follows from, weakly mixing polynomial ergodic theorem, which follows from a result of Chu, Flansikinakis, and Host from 2011. And what it says is that for any L polynomials in ZX, all having different degrees, and any T1 through TL which are weakly mixing, we have that this multi-correlation expression always becomes independent. So here we're assuming that the polynomials are as independent as they can be, right? They have different powers, so that's very independent. Now, the other extreme case is a more recent result by Donoso, Katsuyanis, or follows from a more recent result by Donoso, Katsuyanis, and Sun from 2021. And what it says is that if we have L polynomials, but all of them happen to be the same, and we have that our transformations now satisfy this condition that each of them is weakly mixing, and every pairwise difference is weakly mixing, then we have that for any A0 through AL in A. This expression here also goes to independence. So now, before moving to the discussion about strong mixing, I want to make a remark, and that is that, as I said, all of these results are special cases of more general results. In particular, these two results can be followed first from a result by Donoso, Ferre, Katsuyanis, and Sun, and second by a recent result by Flansikinakis and Kuksa. So, okay, and then so all right, so that's it. Okay, so now we move to but it's fine, yeah. Otherwise no one will know who I mentioned. It's a mysterious paper. Okay, so can we obtain similar results for a strong mixing? So can we obtain this type of results for a strong mixing? And of course, if the answer was no, we will have to talk. So the answer is yes. But first, we need a mode of convergence which parallels the relationship between Euler limits and the weakly mixing pets. So what does that mean? First, it means that our mode of convergence has to be weak enough to allow for potentially non-mixing time. So who knows if those exist, but they exist. And second, it has to be strong enough to be strong enough or sensitive enough to detect an acceptable amount of mixing. right? So first we will go to the weak enough to avoid obstructions. All right, so the first thing is that the usual limits are not going to work. And the way that we know this is by an example due to Lepierre, which states that we can find a strongly mixing Z2 action such that for some A in A with measure 1/2, this limit here does not go to mu cube, it goes to mu squared. So there's some type of dependence in the triple correlation. Now, even though this happens, we have that if you take two monotone sequences, MK and MK in Z, and any A0, A1, A2 in A, one can find an increasing sequence Kj in N, such that sigma J1, J2 goes to infinity of this expression here, which is a triple correlation where instead of having just N as an exponent of S, I have the sum of MKJ1 and KJ2. And instead of having the second N as the exponent of T, I have MKJ1 and NKJ2. So I have the same input in both of them, and the indices come from here. And the point is that this full limit is going to go to independence.
You really mean repeated limit?
Yeah, repeated limit.
Simultaneous limit as J1, J2?
No, so it's repeated, and that's why I need the subsequence. Okay. Yeah. So I need to go to a subsequence to make sure that the limit exists.
And if you switch the order of the limits there?
It will be the same, right? Because the sequences are any.
It's the same increasing K sub J?
You mean like if you put KJ2 here and KJ1 here?
Yes.
Yeah, because it's the same sequence. So this is Ramsey theorem coloring NK and MK. Yeah. And if you switch it, maybe the sequence will be different, but there will be one. All right, and now to aggregate all this thing here, we'll write sigma 2 star limit. And what we mean by sigma 2 star limit is that when we compute any limit of this form, we always get the same value, allowing ourselves to go to a subsequence. All right, so we can get independence along star limits. So a natural question is if sigma 2 star limits are weak enough in the sense that if they can avoid any possible obstruction that will arise when we compute a triple correlation limit of that form, and the answer is no. And the way that we know that is by a recent example that we constructed with Bergelson, which is a measure preserving system XMU, such that with two commuting transformations S and T, such that for any AB in C2, S to the A, 2 to the B is strongly mixing. So we have as much mixing as one could ask at the linear level. And such that for some increasing sequence NK, which comes with the system and the transformations, we have that for some A in A, this triple measure here is larger than mu cube of A plus epsilon. So the epsilon here very likely is large, but the point is that it's larger than mu cube of A plus epsilon. As you can see, the configuration of times which are far away from independence are a set of two summits, right? So we can sum NK1 plus NK2 in any way that we like. So this is not just a sequence which fails, it is a more complicated structure. Now, of course, that means that the sigma 2 star limit.
Define sigma 2 limits.
Yeah, in the previous slide.
Can you show?
Okay. So it is computed any limit with two summits.
The last line where I interrupted you about Kutza. I myself didn't see the last slide, so let us.
But can I ask something?
Right.
So the limit, so you define the limit for any choice of subsequences you have?
So first you choose two sequences. So the quantifiers are for any MK which are monotone, meaning strictly monotone. You can find a subsequence Kj such that you can do this.
Okay.
So another way of thinking of this is that if you take two monotone sequences and you want to be epsilon close to independence, you can find a K1 and K2 such that when you plug in MK1 plus MK2 and MK1 plus MK2, you will be close to independence. So you only need to show that it happens for one MK1 and MK2 for each pair of sequences, and that will give you a sig. If you do it for every epsilon, of course. Okay. So all right, so this doesn't go to mu cube, But the good news are that if we take any three sequences and we play the same game, meaning that we can find a subsequence kj, such that when we look at the same type of limit, but now with three limits, three summands, now we get two independents with three summands instead of two. And the way that we will summarize this fact is by writing sigma 3 limit of this measure is this thing here. Right, so now we have the same thing, but with three summands instead of two, and that's what we write sigma 3 star. Right, so
I have a question. So it seems maybe not obvious from the definition that if the sigma 2 star limit exists, then the sigma 3 star limit exists as the same thing.
Yeah, that's true. So what you could do is you can merge one sequence. So once you know that the limit exists, you merge the first and second sequence, changing the indices. Like for example, what could be like 2K, 3K, you have to pair two of them and the third one let it free, and then there are two sequences. Right. But you're right, sigma 3 star is weaker than sigma 2 star.
Can I also ask a question? Is the definition equivalent if you just take three subsequences? Or is it important that it's the same index in case of J?
You mean if you allow for different indices? So my guess will be that it doesn't matter because you can anyways, if you want to hit one specific sum configuration, you can always force it, right, by choosing the sequences properly. Because what we want is to hit every semi-sum configuration. So if you take anything that is inside of that semi-sum configuration, very likely just with knowing that you can choose infinitely many for each position, then maybe you're fine. That's what I would guess, right? All right, so now this was sigma 3. Well, sigma 3 is here, sigma 3 is here. So now we have a pattern, right? Now what happens if we have sigma L star limits, which are defined in a similar way? Now we can always find this measure preserving system and the commuting and different commuting transformations, SATV, which are strongly mixing for any IB and C2. And an A in A, and a sequence NK in K in N with the similar property that they are far away from independence. So it doesn't matter how large is L, we always can find examples that are far away from independence. Now, as you can see, the degree of the polynomial is important, right? Here we have this polynomial to the L, here we have this polynomial to the L plus 1. Now, the good news is that when we take the sigma L plus 1 star limit of these particular systems, we get to independence. So what are the conclusions? The conclusions are that it seems that any obstruction to strong polynomial mixing is avoidable by taking sigma L star limit with L large enough. The second conclusion is that, as Ethan asked, we have a consistency property that if we take L and L prime and L is less than L prime, then the sigma L star limit of xn is equal to x implies that the sigma L prime star limit of n in z of xn is equal to x as well. So the larger the L, the weaker the limit. And finally, this is just a curiosity, sigma 1 star limit is actually the usual limit because we are checking any subsequence of any given sequence. All right, and this is the end of why sigma L star limit should be weak enough to avoid the obstructions. Now we move to why sigma L star limits will detect a proper amount of mixing. So the following result shows that sigma L star limits are adequate for dealing with the strong mixing. And what this result says is that for any L in N, and any probability space XA mu, and any T1 through TL acting on this probability space, we have that these two properties are equivalent. First, TI is strongly mixing, and for any I different from J, TJ, TI inverse is strongly mixing. If and only if the sigma L star limit goes to independence for any A0 through AL. Or the interesting direction is that the only way in which you can see sigma L star mixing, meaning this type of limits here, is if both Ti and Tj Ti inverse are strong mixing for any I and j. So this can only happen if your transformations are strong mixing and their differences are strong mixing. So in particular, this is strongly mixing if and only if there exists an L in N, such that for any A, B in A, this limit goes to mu A, mu B. Right. So the point is that the sigma L star limits are sensitive enough to detect a strong mixing, because whenever they see independence, that means that your transformations were a strong mixing to begin with. So there's no way of getting around that. All right, so that's the first piece of evidence. The second piece of evidence in favor of the sensitivity or the strength of sigma L star limits is that sigma L star limits are strictly stronger than UV limits. So what do this mean?
Go
Back like here.
So you're saying that if you know that y equals to 1, you know that for every n automatically.
No, if you know that this correlation here goes to independence, then you know that each of them has to be a strong mixing and the pairwise differences have to be a strong mixing.
Yeah, that's actually easy direction. Because in this last expression, you can take a bunch of sets to be the whole space. And then it will fall.
Oh, I see.
Other direction, which is
No, one implies two, is it? And you will, you can replace the ends with polynomials of degree L or something?
No, we know that it's false.
So that's what the starts. You see, this is total analog of, say, my old result was better when it was for Cesaro, and then weak mixing also has similar result. And then you want polynomials with the same nature. Boom, strong mixing is bad for that.
Yes, but if you have some polynomials of degree D, then some SLD limit, or you okay.
So the possibility that getting independence is possible. Getting back to mixing, that's impossible. All right. So, okay. So we were talking about how sigma L star limits imply UV limits. So the first direction connects with what I mentioned at the beginning, which is the sets of finite sums. And the example is if you take a sequence xn, which is 1 whenever n is in this set of finite sums, and 0 otherwise, then the UV limit is 0, right? That's what we said at the beginning. The issue is that now we can take K1 through KL and put them in this sum here. And it turns out that any of these sums is in the set of finite sums. So this xn is equal to 1, which is not 0. So the limits are different, right? So that means that UV limit does not imply the sigma L star limit. And a way of proving it formally will be to see that if you take a different set of finite sums, which is disjoint from the first one, then the limit will be 0. So when you check the definition of sigma L star by checking the sum of L different sequences, you can take first the L sequences to come from here and your limit will be 0, and then to take the L sequences to come from here and your limit will be 1. So that's how you can show that UV limits are not stronger than sigma L star limits. Now, the other direction, I will just say that you have to use additive combinatorics and move on, okay? But the point is that sigma L star limits imply UV limits.
But for any L?
For any L, yeah. Yeah, so this L can be any L.
Which result in additive combinatorics?
Bergelson intersectivity lemma or Poincare recurrence. Right now, full theorem evidence for sigma L star limits, or you can use sets of finite sums maybe, but okay, so full theorem evidence for sigma L star limits. So this will be, typically, this will be our first polynomial ergodic theorem for strongly mixing actions, but this result is so sharp that I decided to quote it as further evidence. So the result is single polynomial mixing for commuting operators. And what it says is that we have two numbers, L and P, any probability space, any commuting transformations, and two polynomials. One of them is x to the L plus P, The other one is x to the L. And we know that T is strongly mixing. Then we always have that sigma L plus 1 star limit of this correlation is always going to be independent. On the other hand, the examples that I showed you before actually give us this here. So we can find a probability space Y beta nu, YB nu, and transformations Q and R, such that for any and B, QA, RB are strongly mixing. But you can find a set A for which this thing here does not go to nu squared of A. Okay, so the reason by which I said that this was sharp is that if you see here, we get independence, right? That is for any any commuting transformations S and T, as long as T is a strong mixing. But when we go to Q and R, we get not mixing. And the reason is the only difference is just L, right? So what this tells us is that if we want to see independence for these polynomials, we need L plus 1 summands, and L summands are not going to be enough. So there's some additive structure needed for getting independence. Right, so that's the last piece of evidence. Now we start stating the strongly mixing counterparts of the weakly mixing theorems that I showed you at the beginning. So the first result is the counterpart to weakly mixing pet. And the statement is essentially the same. We take L polynomials, which are non-constant, and have the property that when we take the difference of any two of them, they are non-constant again. Then we can find an M in N, and such that for any strongly mixing system XA mu T, and any A0 through AL, we have that this limit here goes to independence. So what I wanted to point out is that it says there exists an M in N, and we'll see why that is the case later. And
but I guess it's not the same N if you take limit.
Sorry?
Oh, sorry, I'm sorry, I can't.
Yeah, so the M stands for the amount of additive structure that you need. Okay, so this goes to independence. Now, the second result parallels the result of Bergelson and Lehmann, and the statement is the same almost. So we take non-constant polynomials B1 through BL, and then we can find an M in N, such that for any commuting invariable mu preserving transformations D1 through TL, with the property that any combination of them will be strongly mixing, we have that the sigma M star limit of this expression here goes also to independence.
You can compute this M.
You can
compute this M.
No, I mean it's finite.
And does it depend on the system?
It depends on the polynomials. So,
okay.
So it only depends on the polynomials, and it's independent of the system and the sets.
And the polynomials are linear, he showed for the relativity side.
Or has at least an upper bound, which is the number of sets minus 1.
You could write an algorithm for that.
Well, you show that you can find the corpus.
Yeah.
Like that.
So for people who like bounds, actually, there is astronomical bound for them, if that's what you like.
All right, so now let's go to the next one. So this is the counterpart of the result of Chu-Flatziginakis and Host. And now we take polynomials with different degrees, and then we can find an M such that for any strongly mixing T1 through TL and any A0 through AL, we have again independence along sigma M star limits, of course. And then we have one more result, and this one parallels the result by which was the one? Donoso, Katsuyanis, and Sun. And here we have L polynomials, all of them are equal. Then we can find an M such that if T1 through TL have the property that each Ti is strong mixing and the pairwise difference are strong mixing, then we have that for any 0 through AL, this limit here also goes to independence. All right, so now how do we want proofs? How do one proves any of these results? So the answer is theorems A through C are carried out in a similar way as the weakly mixing counterparts, with the only difference that one has to find a Van der Korput trick, which makes sense for the mode of convergence. And here is the Van der Korput trick that makes sense for the mode of convergence. So we have an L in N, we have a bounded sequence Xn in a Hilbert space. We have L sequences nkj. Oh, well, L plus 1 sequences nkj. And we have to assume that this limit here goes to y in the weak topology of H, and that this correlation expression goes to 0. And then if all of this happens, then that means that y, which is the limit of the sequence that we want, is 0. Now, what is going on in here? So what happens is that because we want to find a lot of mixing, we have to check the small sets, right? And the issue with the small sets is that unlike large sets or intervals, you don't have that much additive structure going on, so you have to pay a price. So each time that we apply van der Korkut, we have to sacrifice one of the summands here and here. And that's the origin of the n, right? Because each time that you apply van der Korkut, you will have to pay the price. And if you want to apply van der Korkut L times, as is the case here, right? Then you will need L plus 1 sequences. That's why I'm starting at 0. Right, so that's the reason of the end. But besides that, the proof of theorem safe through C is exactly the same in the sense of the bookkeeping that you need is the same. Maybe the mode of convergence is different, but that's not important.
But usually you have averages in this path, that you have a Fedel sequence, and if you move it a bit, it doesn't change much. And here I don't see it. So,
Because the average now is in the additive structure. So you are allowed to move one of the terms, which is the one that we're moving here. The n lambda and the n rho. But it's not true invariance, right? That's why there's a price to it, because it's not real invariance, it's just this thing. Okay, so now, okay, so those were the easy theorems. Now let's move to a hard theorem, which is theorem D. And to illustrate how it works, we will look at this expression. So it's F0 Sn squared.
Sorry, can you show us theorem D?
Theorem D, okay. There's theorem D. So theorem D is the one with all the polynomials being the same, and the assumption is that Ti, Tj, T inverse, Ti inverse are also the same. Okay, so let's see. All right, this is van der Korkut, and this is the expression. And we will assume that St and St inverse are strongly mixing, and also that F0, F1, F2 are in L infinity mu, satisfied that the integral of F2 is 0. Right? So what we want to show is that along some type of limit that we don't really care about, we have that this is going to 0. So I will just show you the algebra, not the limits. And roughly speaking, what we want is to prove that after applying repeatedly a generalized version of van der Korkut, so the van der Korkut that I show you is not enough, but there's a van der Korkut that is enough, we arrive to an expression containing only linear powers of St and St inverse. So what I would mean by linear will be explained later. St and St inverse as opposed to what? So if we have St to a -2, that is not the power of St inverse, right? So we don't want to see those things in there. And the reason is that all that we know is that St and St inverse are strong mixing, so we should not see any other type of expression after applying van der Korkut many times. Okay, so the proof is divided into 3 steps. Step 1 is applying the usual PET induction. So we start with this expression here. And then what van der Korkut says is that you have to add L1 and R1 and R1 to each of the terms. So we add L1 and R1 to each of the terms. Then simplify, get this. So first we add L1, R1, L1, R1. Simplify, we get this. We do it again. We get this thing here, which now I have to use some notation. So sigma 2 is either L2 or R2, and sigma 1 is either L1 or R1. All right, so we get there. We apply van der Korkut once more, and we arrive to this. Okay, so that's bad. And we have to list all possible choices of L1 or R1, L2 or R2, L3 or R3 as sigma j's, 1, 2, and 3. and j goes from 0 to 7. Okay, so what do we do with this expression? So we look at it and then decide what is going on. So the first thing that is going on is that we finally arrive to linear, right? So you see here, n has degree 1, and n here also has degree 1. So that's good. Now, what is bad is that if we look at a specific instantiation of sigma j1, sigma j2, sigma j3, r1, r2, r3 equal to r1, r2, r3 into this terrible expression here, I'm ignoring these terms because they will disappear eventually, so they can be ignored. Then when we plug in r1, r2, r3, we get this thing here. And as you can see, this is not a power of t, it's not a power of s, and it's not a power of st inverse. Okay, so we need to work more. So we apply van der Corput 7 more times, and we get here. Okay, and again the same. So all expressions are not all the expressions are powers of st or st inverse. And an example is here. We take L1, R2, L3. You will see that this is this. Right now, what happened here is that we got 2 to the 7 parameters, which are either lambda t or rho t. So yeah, so they are here, gamma ij, gamma tj, gamma tj. And those are the lambdas or the rhos. And I will next simplify this expression to explain how we can move to step 3. So this was step 2. So if you look at this expression, what is going on is that we have an operator here next to gamma tj, and we have another operator here next to gamma tj, right? So essentially, the way in which this expression is constructed is that we pick an element of this set, and then we put it in there, right? And
Why is this bad again?
oh, because the expression here is not a power of t, st, or st inverse.
So it is like KS inverse instead of ST?
No, because this is t to the 2r1 minus l1 and r3 minus l2. So it is not a power of, yeah. So
for the theorem also not. That's what it's saying.
yeah, this one is also not good. Right, so now what do we do with this? So as I said, we have to look at the structure. So the structure is, as an operator here, gamma tj, another operator here, gamma tj. Okay, so what we will do is we will try to untwine st and st inverse in one. So they are entwined, as you can see here, they are entwined in some way. So we'll try to entwine them using van der Corput, but now we will apply it to the parameters. Okay, so this is the example that I constructed for explaining what is going on. So I fix an operator here, I fix another operator here, same operator as above, same operators as above, same operator as above, and this column also has the same operators, right? And then I place all possible choices of lambda 1 and rho 1 and lambda 2 and rho 2. So it has essentially the same shape as before. And now this expression here is in red because I will simplify a little bit by factoring it out. And after factoring, I have this expression here, which I will copy now in the next slide. Okay, so we start with the factored expression. And what we will do is we will apply van der Corput to R3. So there's R3 here, R3 here. And as you can see, the red expression has no R3, right? So after applying van der Corput, the red expression will disappear and will be here. Then we simplify a little bit and we finally arrive to our destination, which, as you can see here, we have t to some power, t as inverse to some power, and t to some power. Now, the reason this is valid is because if you see here, you have lambda 2 minus rho 2, and here you have lambda 1 minus rho 1. So you are allowed to separate between lambda 1s and lambda 2s. Okay, so now all of the all of the expressions are powers of st or st inverse. So now, just to show you why we wanted to get here, I will finish the, I will take the limit. Okay, so here's the last expression in the last slide. And here we have the limit. And what this tells us is the order in which they go to infinity. So the first one to go to infinity is rho 2, and the last one is L1. So because they go to infinity in different order, one can assume without loss of generality that R1 minus L1 is positive, same as R minus L. And we can send first R lambda 2 minus rho 2 to infinity, and then lambda 1 minus rho 1. So what happens when we do this is that the first thing to go to infinity is this guy. After sending that guy to infinity, because TS inverse is a strong mixing, we will get to this product. And then we send this guy to infinity, and we get to that to a fourth, which is 0, because by assumption F2 had integral 0. Okay, so this was just an example, right? So this is not really that useful, but at least it shows why we want to get to only powers of ST and ST inverse. All right, now we go back to the original expression. And the example that I showed you is fairly simple, but it shows that we can untwist the T and the TS inverse, meaning that we can isolate TS inverse or T or any of those. And there are many possibilities. For instance, maybe the blue part is not in there, so we're already fine. Or maybe the red part is not in there, so we're fine. But when we have both parts, we'll have to apply van der Korput. It is true that there will be some extra interactions that one has to be careful with. But at least it is believable that by applying van der Korput to the parameters, we will eventually get only powers of TS and ST inverse. Right, now, what is the new issue? The new issue is that in reality, we want to prove more general results. And there are only two options. One is one develops a very efficient algorithm for computing van der Korput after many steps, and that is not good. And the other option is to understand how it is that each time that we apply van der Korput, what happens with S and T. So we will do the part of understanding how van der Korput entwines the transformations. And just as a remark before moving, we actually have results for different polynomials here. And essentially our results are the weakly mixing the strongly mixing counterpart of the results of Donoso, Ferrer, Katsuyanis, and Sun, but only for one parameter n as opposed to many. They have it for many, we only have it for one n, but that's the best way of explaining what we can do. So that's how far this method goes. All right, so now what is the lemma behind the untwining of the S and T's? So here it says, how van der Korput entwines S and T? So the lemma behind the understanding is this observation here that very likely anyone who has done induction has seen. So if we have two polynomials u and u0 in Cx, and we form v equal to u minus a0, and w in Zx h1, h2 is defined by this difference, then if we assume that there's a v in n for which our polynomial wx h1, h2 is equal to this sum here. So the coefficients AWS, H1, H2 are polynomials in two variables. And when I say that it's non-zero, I mean that as polynomials in two variables, they are non-zero. So if that happens, then we know that the degree of u and the degree of u0 is less or equal than d plus 1. The degree of v is less or equal than d. And more interestingly, if we set u of x equal to this polynomial here, and v of x equal to this polynomial here. So essentially, we're defining what are the coefficients. Then what we will call the leading coefficient of w, which is here, will be defined by the leading coefficient of u, which is here, and the leading coefficient of v, which is here. And as you can see, we have some h's here. That means van der Korput. So that is good. And we have v here, and v was just a pairwise difference of two polynomials. Okay, so what is the idea for the general case? So the idea for the general case is the following. So we start with the step one, which is usual induction. And so we start with some expression that I will call expression 1. Then we apply van der Kerkhut many times, and we get to expression n. And then apply van der Kerkhut once more, and we get to expression n plus 1. Okay, so that's the end of step 1. Then we apply step 2, which was just the crazy application of van der Kerkhut to get to this expression with 2 to the 7 terms. And we get to some expression that I will call multilinear 1. Okay, so well, this is terrible, but okay. So if one thinks of this, expression n plus 1 and multilinear 1 are connected, right? Roughly speaking, all the coefficients of all the powers of t, s, and s inverse, or all the combinations in there, come from expression n plus 1. So what we did in the example is apply van der Kerkhut sometimes to change the coefficients of expression n plus 1 to something that is related with expression n. So we can van der Kerkhut a lot here, and now get to expression, multilinear 2. And how do we know that we can van der Kerkhut to get to multilinear 2? The way in which we know is because of this here, right? We know that we can always apply van der Kerkhut to h1 minus h2, and that will move us up one step. Now, this expression multilinear 2 is related with expression n, right? And all the information that we have in expression n comes from expression n minus 1. So here's expression n minus 1. So if we van der Kerkhut a bit more, we will get to multilinear 3, which has coefficients which are somewhat related with expression n minus 1. And then if we continue in this way, we will get to expression n plus 1, which has coefficients related with expression 1. And all the connections are made via this identity. But of course, to have something so nice, I have to align. So the truth is a bit harder. The truth is that the way that we play this game is that we start with any potential expression n plus 1, and then we show that any potential expression n will have nice mixing properties. Okay, so we start with expression n plus 1. It has nice mixing properties. That means that any potential expression n has good mixing properties, and that means that any potential expression n minus 1 has good mixing properties, and so on, right? So what I'm saying is that, let's say the intuition is that first you move down via pet induction, you move to the other side, and then you move up by applying van der Kerkhut. But the truth is that you need some extra information, so you have to push it down from the top. And that's the end of how the proof works. Now there's a final remark about how our methods can be adapted to obtain weakly mixing and mildly mixing results. And the reason is that our techniques are very algebraic, right? If you see here, I don't really care about the mode of convergence. As long as it's with convergence, it's fine. So any of the classical mixing notions will be fine. Okay, and in order to obtain these results, one needs, the way of obtaining the results is to compute the relevant limits along sums of ultrafilters on Z with desirable properties. The table below it states the properties that make an ultrafilter adequate for each mode of mixing. So first, a strong mixing. The type of ultrafilters which are good are non-principal ultrafilters. that means that every element of the ultrafilter is infinite. The second one is mild mixing. And what makes nice an ultrafilter for mild mixing is that it can be written, so P can be written as the sum of Q plus R, where Q is idempotent and non-principal, and R is anything. So, and finally, weak mixing is any ultrafilter that has the property that each of its elements has positive upper Banach density. All right, so now just for showing how this will look, this is theorem A prime, which is the counterpart of theorem A, which is the strongly mixing counterpart of weakly mixing PET by Bergelson. So the first result that I show you. And it reads essentially the same. We have the L polynomials. All of them satisfy the condition that they are non-constant and the pairwise difference are non-constant. And then we can find an M such that for any strongly mixing system and any non-principal ultrafilters P1 through Pn and any A0 through AL, we have this limit here. Okay, so this result here looks a bit worse than the sigma M star limit that I showed you first. So the first version of this theorem, of theorem A, it looked exactly the same, except that instead of having this sum here, it had just sigma M star limit. Okay, so what is the advantage? The advantage is the following. So by just changing the word strong mixing and changing the place where I'm picking the ultrafilters, I get the weak mixing version. Of course, I have to define what is D. So it is defined here. So if we let D be the family of all ultrafilters with the property that if A is in P, then it has positive upper Banach density. Then the theorem, the weakly mixing PET, looks the same as the strongly mixing PET, except that it says weakly mixing here, and it says D here, right? And maybe you can erase non-principal, but I left it there. So, right, so that's the only difference. Now, to show that this is actually the same result as weakly mixing PET from the beginning, you actually need an extra fact. And that is that for any M in N and any E inside of C with positive Banach density, we have that there exist M ultrafilters in D, such that E is in the sum of the M ultrafilters. So there's something to be done in order to show that this is the same as weakly mixing PET, but it can be done. And with that, I am done.
Thank you. Are there questions, comments?
So you had 2 more pages there.
Oh, but that is just because there's that page. And the other one will be something crazy.
Oh,
What's that? Can I ask you one question? So in this result of, let's say now, Donoso, Feremo, Rages, Kutsogiannis, I got them on the...
And soon, yeah.
Soon. And soon, yeah. So they do PET, and then they use the concatenation of Tau Ziegler, they had to. And you seemed with some different PET that you avoid this. Is this the case?
That's what I think. So
Is it the case that perhaps your PET, if the modification of your PET in your case would avoid also the concatenation?
So
Because the point is that they have on the first step, they let's say they want to isolate, as you said, the TS inverse, and they have some other mixes, and then they use the concatenation just to remove this. And in your case, you didn't mention anything about Tau Ziegler concatenation or anything. No, but it's still a PET that you do. It's not.
it's
Okay.
very cumbersome by necessity.
Yeah.
That was
Okay, that's interesting. So perhaps
Playing
it could be done. I mean, it was always a possibility that it could. Good. And the second one is, so I guess you didn't try the pairwise independent that we have also with Kutsa.
that I don't know because you use invariants, right? And with mixing, you don't have invariance.
No, there is no invariance for this. If you have pairwise independent polynomials, pairwise, one is not multiple of the other, and weakly mixing, then you go to the product of the integrals without invariance. Let's say n square plus n. This case, you could do?
No.
Not n square n to the third, n square and n square plus n.
Yeah, I know, no.
Okay.
Well, it depends on the assumption. If you just assume that T is a strong mixing and let's say T and S are a strong mixing, then no.
Okay, yeah, only with this assumption. Yeah, that's what I mean. Yes. But it should be true.
But the issue is that we cannot, because we don't have factors, that when you make the ping pong argument, we
Okay, so you try this.
not enough. I want to think that maybe you can do some algebra with the independence, but I don't know.
But what's really the main thing, we avoid analysis of factors because we have so cumbersome but working path induction, variation of path induction with variation of undercore.
Yes, it's not that we use any information for this argument about the factors. You don't. It's a very soft argument. Okay, anyway, it's good. Good and complicated anyway.
Okay, any other questions? Let's thank Rigo again.